This is the last topic of your option, and we are going to look at stereochemistry of some of these molecules. It helps if you look at your organic chemistry and refresh what stereochemistry was all about. This is what you need to understand, and this is how you need to apply your understanding, so you can slow down and take some notes. But the first molecules we are going to look at are amino acids. Table 20 of your booklet talks about your amino acids that you need to know. They are known as 2 amino acids or alpha. The second carbon has the attachment R, your free radical, or the chain that changes. And if you look at all these second carbons, you see they have 4 different attachments. The hydrogen is also different. So these are chiral carbons, or they are possibility to produce enantiomers and optical active compounds. There is only one amino acid that is not optically active, and that's glycine, and that's the carbon that has 2 identical hydrogen, therefore it's not chiral carbon. So all your amino acids, by the way, are L enantiomers because they rotate plane of polarized light to the left hand side. Now we need to be able to decide if it's L or D, and we are going to apply Cohen rule. So the first one, alanine, I drew it 3-dimensional. The hydrogen with dashed line is in the back. Now COOH, your carboxylic group, is the CO of the Cohen. Your CH3 is your R group, and finally your amine group is your N, and you see it spells out as Cohen. Now if the Cohen is spelled out in a counterclockwise sort of rotation, we are going to call this L amino acids. In the other, if you look at the other mirror image of this, which is the other optically active, the Cohen is spelled out in a clockwise fashion. Therefore, this is your D enantiomer. So that's basically how you need to designate L and D amino acids, and that's the limitation of what you need to know. For lipids, we have to worry about cis and trans. The cis version, the hydrogens are on the double bond are on the same side. For the trans, the hydrogens are across from each other. Trans has higher melting point because what happens is the next strand of molecules, they can pack to this really nicely, and you could have your intermolecular forces of London dispersion just holding on to this molecule. If we look at the cis, because of this 120 degrees sort of a angle, you are not capable of having nice packing. Therefore, the London dispersions are not as strong as the trans version, and you have lower boiling point in that case. Now, if you also recall from organic chemistry, what we can do is add hydrogens to the double bonds. Electrophilic addition, when you have nickel catalyst, you add hydrogens, you can saturate this, and the double bond turns into a single bond, and they are saturated with hydrogens. So what happens when we add hydrogen to a fatty acid? If it goes through complete hydrogenation, you turn it into saturated fat, and it's just single bonds, they're all carbons. If it's partial hydrogenation, you might produce some saturated fat, but there is also possibility of inversion of these carbons to give you some trans version, and these trans fatty acids trans are not healthy for us. So when they go through partial hydrogenation for the cis, you will get some saturation. At the same time, you also might produce some trans fatty acids. For carbohydrates, we are only going to look at glucose, C6H12O6. The linear version of glucose, which is an aldehyde, the first carbon and the last carbon, these are not chiral. But the rest of carbons have 4 different attachments, and those are chiral carbons. The last carbon away from the aldehyde, which is carbon number 5, if the hydroxyl group is on the right, when you look at it, right hand side, that's indication you're D-glucose. Now what is the L-glucose? When you take the 5th carbon and you put the hydroxyl on the left. So if it's on the left, this is indication that this is L-glucose. But when you do that, make sure you respect the rest of, this is a mirror image, so all the hydroxyls should be on the other side when you're looking at them. So not just the last one, but the rest of hydroxyls are also flipped version. But the fifth carbon is deciding if you are right-handed, D, or if you're left-handed, L. Now what happens, they also sometimes in aqueous solution turn into cyclic. So the oxygen of the fifth carbon and the first carbon, they form a bond. It's not dehydration, synthesis, or condensation. It rather gives you a cyclic form with an ether linkage in this fashion. And this is your carbon number 5, and this is your carbon number 1. On the carbon number 5, we have CH2OH, so it shows up here, CH2OH. Of course, there is a hydrogen here. Then on all of these attachments, this is what you have. OHs are this. If you look at the first carbon, if the OH is same as this side of carbon 6, this is example of beta glucose, the cyclic form of that. Now what happens, it can go back to straight chain and then it can get inverted again to give you the alpha version of it. The only distinction between alpha and beta is the carbon 1, that instead of the OH to be on the same side as this, is going to be on the flipped side, on the opposite side. The rest stay as is, as alpha. And this is your, as your beta, sorry. And this is your alpha glucose. Now, to summarize this, I'm just going to give you a cleaner version of it. So this is D-glucose. Now, if you produce in aqueous solution, it will be cyclic. If the OH is on the same side as carbon 6, then you're beta. If the OH is opposite side as carbon 6, then you are alpha.